Hey everyone, welcome back to Mind Maths with Amina. In today's lesson, I'm going to derive the new Keynesian Phillips curve. A quick disclaimer before I start. This video contains heavy mathematics, the serious kind of maths, the kind that might make you question your life choices. But I'm going to try to keep things slow and take everything step by step. So let's hope you survive this class. Okay, let's begin first by I've decided not to record lessons which require prior knowledge. So I want each lesson to be like a standalone. So before I actually start deriving the Phillips curve, I'll introduce, or basically for most of you, it's just a revision of some of the concepts that we need in order to derive the Phillips curve. So let's just firstly talk about linearization using a Taylor expansion. So for instance, suppose we have a function which is a ratio of optimal price and actual price given like this. P star T over PT. Whatever example I'm going to write when I'm like revising a concept, this will come into usage when we are deriving the Phillips curve. So it's nothing extra. So if I define a function g, P star P as the log of the function f, this is basically just the deviation of price from PT. Okay, so if at the steady state, if I say in the steady state, the optimal price and the actual price are all equal to the long-term price, then our function g is the log of function p bar over p bar, which is just ln 1, which becomes a 0. Okay, so remember, I want to linearize this function around the steady state. Just a revision, if you have a function, let's suppose g x y, then the Taylor expansion is around the steady state. Let's suppose I'll call it x bar y bar is g x bar y bar plus the Jacobian at these two. So the Jacobian would be, let's just write it, the Jacobian of the function around x bar y bar into the deviation of x from its steady state value and deviation of y from its steady state value. And I'm not going to take higher order derivatives, because then that would we'll end up with a square. And remember, I want to linearize it, so I don't want higher order derivatives. So this is basically like the Taylor expansion. For instance, if this was just function of one variable, then I would have written g x bar plus the derivative of g x when x it takes the value x bar and multiplied by x minus x bar. And then, for instance, the double derivative at x is equals to x bar, then x minus x bar square over 2 factorial and so on. That's the Taylor expansion. But I'm doing the Taylor expansion with the highest order being 1, because I want to linearize my function. Okay, so I'll just make a box around here. So let's start linearizing the function g. P star T, PT. P star T is the optimal price, PT is the actual price, which is ln P star T minus ln PT. So the derivative of G with respect to P star given P star takes the steady state value is going to be 1 over P star, and instead of P star we have to substitute the steady state value. Similarly, the derivative of G with respect to P when PT takes the steady state value P bar, then it's again minus 1 over PT, and PT takes value P bar. Okay, so a linear approximation would be GP star comma PT is approximately equals to G P bar plus column vector, no, a row vector, yeah, G derivative of G with respect to P star when P star takes value P bar, and the derivative of G with respect to P and P takes value P bar. So this multiplied by the column vector. Okay, so deviations from the long run, it's going to be P star minus P bar and P minus P bar with time in the subscript. So let's open this up. We'll have a G P star comma P star plus, okay, what was this actually? Let's add another step. We've already calculated the partial derivatives. This was equals to 1 over a P bar, and this is minus 1 over a P bar. Okay, so therefore we get a G P bar P bar. Remember, this is a 1 by 2 matrix and this is a 2 by 1, right? So we're going to get a 1 by 1. So it's just one entry, sort of like the inner product. So 1 over P bar into this, right? Minus 1 over P bar into this. Okay. So we calculated the value of G, P star and P at the steady state, which was equals to a 0. So I can put a 0 there. So it's going to be a 0 here. Then I have a P star T over a P bar minus P bar over a P bar, which is just a 1, minus PT over a P bar, yeah, it's a P bar, plus P bar over, which is a plus 1. So this gets cancelled out, and therefore we have a 1 over a P bar. So this is the linear approximation. Okay, so for instance, how do I explain it? For instance, let's just make a side note. Whenever you're doing the Maclaurin series of EX, right, it's going to be like a 1 plus x square plus over 2 plus x 3 over 3 factorial, I believe. Yeah, and it just basically goes on and on. But this is not a linear function because there's a square here, there's a cube here. So if I want a linear approximation, I'm just going to keep it at 1 plus x. Okay. Similarly, when we are doing the linear approximation for 1 plus x, if I do the Maclaurin expansion around x is equals to 0, I'm going to get an x minus x square over 2 plus x3 over 3 minus x4 over 4 and so on. But this is no longer linear because of the square and the cube and the power 4, right? So if I want a linear approximation, I'm just going to leave it at x. So for instance, if I see a log of 1 plus x and I know that x is a small number, so it's a fraction, then I'll just say it's approximately equals to an x. So this is known as, like, you're using the Taylor series to approximate a function, but because I needed a linear approximation, I will not take higher orders of this function because then my function will no longer be linear. Okay, so these are linear approximations using Taylor expansion, and what we found out right now is that if I have a function which is ln of p star t over a pt, right? This was my function g p star comma p. It is approximately equals to this. This is a linear approximation of the log of this ratio. Okay, and it's linear because I didn't take any higher orders of this. Okay, so at this point we're going to do an algebraic manipulation. I'm just going to add and subtract p bar, because remember when we're going to do the what were we doing, the Phillips curve derivation, even the IS derivation that I did previously, the new Keynesian economists are basically interested in the deviations of output or consumption or any variable, for instance price, from the long run value. So since we are interested in the deviations from the steady state p bar, so I'm going to add and subtract. So I'll get a p star t minus p bar, and I'll have to add one as well, but let's take pt as common, so I'll have to put a minus sign here because I need to add a p bar, and I know a minus into minus is a addition, so I have a plus p bar and a minus p bar. Okay, so according to our terminology, I can write this as p star hat t minus p hat t. I just said in the beginning of the lecture that I am going to make standalone videos, and here I am again assuming that this terminology is known. Let me actually rewrite this. If I say the small y, for instance, is usually used as is the log of the aggregate value. Okay, and if I say y hat t, that is just ln y t minus ln y bar, and this shows the deviation of output from long run level, and in this case the long run level was y bar. Okay, so whenever you see a small letter and a hat over it, then that's basically just deviations. Okay, so this is deviation. Okay, moving on. Where were I? Okay, the next thing is that p star, what did we write? Let me rewrite this. We discovered this, yeah. So remember that ln a is equals to b. Ln is always to the base e, right? So that means e power b is equals to an a. So if I use this, I'll get an e to the power p hat star t minus p hat t is equals to p star t over pt. And since e power x according to the Taylor expansion around x is equals to 0, a linear approximation would be a 1 plus x. So therefore I can write this as a 1 plus this is equals to a p star t over a pt. So from this exercise we've learned two things, that the logs of the ratio of p star t over pt is equals to p hat star t minus p hat t. And the second thing that we've learned from this is that the ratio of price itself is approximately equals to this. Now take a 5 minutes break to absorb all of this. Just one more thing before you take a break is that you would ask how I jump from here to there and here to here, right? So somebody like, this is a valid question, how can I make this expression equals to this one and this expression equals to this? Let me show you. Basically we know that p hat t is ln pt minus ln p bar. Similarly, p hat star t is ln p star t minus ln p bar. Both denote the deviation of price from its steady state. Okay, if we have a function of one variable and I want a linear approximation around the steady state value bar, then I'm just going to take the first derivative at x bar and I'm going to multiply it by x minus x bar, and that's it, right? So if I have an ln p star, right? So the value of this function at the steady state is just ln p bar plus the derivative is 1 over a p star, right? So at the steady state the p star value is a p hat p bar, and then we have a p star minus a p bar. So therefore we get ln p star t minus ln p bar is equals to this expression, right? And on the left hand side you can see that this right here is just the deviation of the price, optimal price from the long run value. So therefore this happens. Okay, so the reason why I replace this with the deviation of price from its long run level is because I use the Taylor expansion once again. So similarly, when we had on the right hand side, what was it? Okay, pt minus p bar over p bar. Okay, so if I have a 1 over p bar and we have pt minus, sorry, it's a capital, pt minus p bar, then it's just going to be a p hat t, right? So that's why I was able to replace those two expressions. Don't get confused that there aren't any logs over here, so why did I put a hat over here? Because technically in order to show change we need logs, but I used the linear approximation once again to be able to write that. Okay, now you can take a 5 minutes break. Okay, so now that you've taken your break, there's going to be when we're deriving the Phillips curve, we're going to end up with this optimal pricing rule, which is, as you can see, it's non-linear. And we cannot use a non-linear optimal price, for optimal price as a function of a non-linear equation in our derivation. So we have to linearize this as well. So let's start doing it. Remember that in a steady state, the marginal cost is equals to epsilon minus 1 over epsilon, which is just given, and the value of p star is p bar, and pt is also going to be p bar. So let's take the ratio p star over t over a p bar. Okay, so this just comes here as it is. On the numerator and denominator, we're going to make some changes. Okay, take a deep breath. I hope this doesn't look scary. Each of these is of power epsilon, right? So if I do divided by p bar over here, sorry, this remains there, I'm just going to do a whole power e. If I'm doing something in the numerator, I have to do it in the denominator as well. So I'm going to divide this by p bar as well, and there's a e power e minus 1, and therefore it's just like dividing the whole thing by a p bar. Okay, because an e minus e plus 1 is just a plus 1, so technically you're just dividing the whole thing by a p bar. Okay, so on the left hand side, we can do we're going to do logs on both sides, right? Because we've already derived, we've done the linear approximation of this ratio, so I can use that on the left hand side. So I'm going to do apply logs on both sides. So let's just see what the left hand side is going to look like. So if I put the logs on the left hand side, we just found out that this is equals to, what was it, this. Okay, so let's write it. It's just a p star hat t minus a p bar. Okay, bar is just a value, so it's not gonna I don't need to put a hat on it, so it's just a p bar, I think. Yeah, so this goes here, and on the right hand side, let's take the logs on the right hand side. These things are this is being multiplied, and a division, and there's a division sign, right? So for instance, an ln a b is the same as ln a plus b, ln b, right? And for instance, if we had ln a b over a c, then it would have been ln a plus ln b minus ln c, right? So let's use the log rules over here. So what I'm trying to do is I want the log of this whole expression. Okay, so let's do that. Let me just move on to the next page, actually. The dread. I have a very deep feeling that this lesson isn't going that well. This kind of mathematics I do well when I'm just doing it on my own, but it's kind of difficult to solve something and talk at the same time. Okay, so these are being multiplied, so I'll do, and the summation sign can go out, the constant can go out, and the logs can get applied here. So I'll get a log of the marginal cost t plus k. I'll explain what this means when we start the model, so don't worry about that too much. Plus ln of this ratio. Actually, let's just use the power law. Remember, the power law is that ln a power b would be b ln a, right? So the power is epsilon, so I can just write epsilon there and keep the ratio. Okay, then we have a plus ln yt plus k. Phew, that's done. And it is k goes from 0 to infinity. Okay, now the division sign becomes a negative sign, and then we do summation again. B theta is the same, k from 0 to infinity. Then we have, okay, we can use the power law again. So let's do the power law. I'll get an e minus 1, and then what did we have? Okay, then the log of p t plus k over p bar. Is there any y here? Yes. Plus ln yt plus k. Okay, when we open this up, this easily, like this whole expression and this is going to just cancel out. So like what I can see is this is going to disappear, right? And what else? We have an epsilon ln this, and we have, okay, let's just open this up then. Okay, let me rewrite it. So this remains here, this remains here again, right? And oops, and we have this expression. I'll close the bracket, minus, let's kind of minimize this so this fits in my whole page, and I'll have this now. But again, I can just what we can do is that I can multiply the epsilon over here, and basically I'm just opening up the bracket, so we'll have this again. Okay, oh, there's no epsilon. Okay, the log of this. So now there are two expressions that again can get cancelled out, which are these two, because we have a plus sign associated with this expression and a minus sign associated with this one. Okay, okay, what else? Yeah, so okay, moving on. So this expression becomes, actually, why am I like, I know that the right hand side and left side are equal to each other, right? So instead of writing the ln of this, I should just replace it by this, because the left hand side and right hand side are just equals to each other. So it will save me a lot of space if I just use the fact that the left hand side has to equal the right hand side. Okay, yeah, it looks much better. Okay, so the left hand side equals, okay, now we have ln epsilon e minus 1, okay, plus summation k goes from 0 to infinity b theta power k, and we have ln mc, and that's basically going to be the same as, let's just leave it there, I think, for now. Yeah, let's just leave it there. ln mc t plus k minus summation b theta power k k goes from 0 to infinity, and a minus and minus will become a positive. Okay, a minus minus becomes a positive, and we'll get an ln pk pt plus k over p bar. Okay, and this we already know is equals to a p hat star, right? Okay, now this is the equation. Let me copy paste it here. And we want to see, because we're the point of doing all of this was to see we wanted to log linearize around the steady state, right? It's a t plus k. So I want to write this equation, the value, what this equation will look like in the steady state. So remember, in the steady state, the value, there's not going to be any change in the level of price, right? Deviation, there's going to be no deviation. So this is just going to be a 0. Again, this is going to be at the long run level, and there's going to be there's going to be no deviation over here, so this becomes a 0 and everything gets multiplied by 0. So now what I want to do is I want to subtract the second equation from the first one. Okay, and when I do that, this will get cancelled out, this will get cancelled out, and nothing else get cancelled out. So I'll be left with a p hat star t is equals to a summation beta theta power k and log of mc t plus k minus ln, because remember we were subtracting, so the signs technically change. This becomes a plus, this becomes a minus, this becomes a minus, so it's going to be a minus ln mc bar t plus k, and this just stays where it is. Okay, and now we have p hat star t is equals to summation beta theta k. Remember, this is the deviation of marginal cost from its steady state, so that's simply an mc t plus k hat, because that's the deviation. They have the same coefficient, so we can just write this as plus p hat t plus k, and voila, we are ready. This is the linearized, let me write it down actually. So we've made it this far, which is a big deal. This is the linearized version of the pricing rule. And remember, it's linearized, it's actually log linearized around the steady state, okay? And it is the pricing rule, and this is what we're going to use in the derivation of the Phillips curve. Now I would like for you to take a 5 minutes break again. Okay, I'm back. Let's continue. I hope everybody actually did take a 5 minutes break. I did. I had a pizza and it was refreshing. Okay, so let's continue. Below is the non-linear aggregate price index under the Calvo pricing. This is what we're going to be using in our Phillips curve derivation, but we cannot use the non-linear version of the aggregate price index. We need to linearize it, okay? So in the previous section, we had the optimal pricing rule, and again, it was non-linear, okay? So this was the non-linear version. We had to linearize it, And when we did get an expression like this, it was still written in levels, and we wanted it in terms of deviations only. Therefore, I wrote the same equation on the steady state, and I subtracted it to find the deviations, which basically helped us get rid of all level variables, and we ended up with the log linearized version of the pricing rule. Now that the pricing rule is, we have the linearized version of it from k0 to infinity, we need the linearized version of the aggregate price index as well. So let's begin. Let's write the ratio first. So PT, let's divide the left hand side and the right hand side by P bar power 1 minus epsilon. So on the left hand side it's divided, so I'll have to divide it through on the right hand side as well. So the reason why I'm doing this is because I know next I can apply logs, and as a consequence I will end up seeing the difference actually the difference of a level from the steady state. So this is a P star T over a P bar power 1 minus E. So basically we divide it through by P bar 1 minus E. P bar 1 minus E, epsilon actually. Okay, so now let's take the logs. We can use the power law. The power gets multiplied, and I'll have an ln pt over a P bar, which is the deviation of the price from the long run level. And then we'll have an log of this whole expression right here. Okay. Okay. So on the left hand side, I have 1 minus epsilon, and this is just the deviation of price from the long run level. And now we need to figure this one out. Okay, what we know already is that we said any change in price from the long run level is written like this: pt minus ln p bar, which is the same as ln pt over p bar. Therefore the ratio pt over p bar is just e power p hat t. So we can just use this fact over there. So let's do that. I'll have an ln e theta e power p t minus 1 hat, right? And the power can get multiplied because even the power of even an exponential, no, this is actually just a power e. Yeah, so you can just multiply it. Yeah, so I'll have a e 1 minus epsilon into p hat t minus 1. Similarly, I'll have a 1 minus theta. It's so hard, I like to talk while you're solving math. It's difficult because I keep losing track of what I have to do because I'm speaking at the same time. 1 minus epsilon, and this becomes a p hat star t this time. Okay, so far so good. Now what? Another lead approximation that we know is stated in the same lecture actually, is that when you have e power x, it is approximately equals to 1 plus x. Therefore, if I have a e power 1 minus epsilon p hat t minus 1, it's the same as 1 plus 1 minus epsilon p hat t minus 1. Okay, so let's use this fact. I'll have an ln theta 1 plus 1 minus e p hat t minus 1 plus 1 minus theta 1 plus 1 minus e into p hat star t. Okay, good. Let's move this on to the next page. Why did I change the color? Okay, let me copy paste it down. This is what we have so far. On the left hand side, I have a 1 minus epsilon p hat t. Okay, let's open the brackets up. I'll get a theta p hat t minus 1 plus 1 minus epsilon into theta p hat t minus 1. Okay. Oh, this is so long and so annoying. Plus, okay, it's a 1 plus 1 minus epsilon p hat star t, and then a minus theta into, what am I doing? This wasn't getting multiplied by that, was just a theta. Okay, this was just a theta. Theta into this, theta into that. Okay, this as it is. Okay, theta into the first expression and minus theta into the second expression. Okay, my bad. Okay, so this cancels out nicely. And what else? Why do we have a 1 here? Okay, this one got multiplied. Okay, let's write this down. We have an ln of a 1, so I'm just writing the 1 here, plus if I take 1 minus epsilon common, I'll get a theta p hat t minus 1 plus 1 minus theta into p hat t star. Yeah, good. And remember, since for small values we have ln 1 plus x is the same as x, so since we have a 1 plus x, this is a small number, therefore this is going to be equals to this. You can imagine why this took me so much time to figure out. I literally almost just lost my mind doing this. So it'll be quite a sad thing if the professor doesn't even teach this in the end. Okay, so we just ended up with the linearized version of the of our price index. Okay, we had a 1 minus e p hat t, which is the deviation of price from its long run level. The 1 minus epsilon gets cancelled out, and then we're left with a p hat t is equals to theta p hat t minus 1 plus 1 minus theta into p hat t star. Okay, so this is now the linearized Calvo aggregate price index. So what we've achieved so far is that we have the linearized version of the optimal pricing rule, which is what we need in order to derive the Phillips curve. So we've done this, and we need the linearized aggregate price index, and we've done this as well. Okay, before I move on, and I'll obviously give you a 5 minutes break again, I just wanted to talk about this linearized version because in new Keynesian economics, we have on the vertical axis, we're basically dealing with inflation, right? So inflation is going to be defined as P hat T minus P hat T minus 1, okay? Um, should I tell you why though? Uh, you can just plug in the values of this and you'll see it is actually exactly equals to inflation, okay? So I want to convert this in terms of inflation. So if I subtract P hat T minus 1 from both sides, I'll get the following. I'll get a P hat T minus P hat T minus 1 on the left hand side. I'll get a theta minus 1 P hat T minus 1 plus 1 minus theta P hat star T, which is I have a inflation on the left hand side. I'll have a 1 minus theta. Theta is usually less than 1, so I'm going to take 1 minus theta out as common, and therefore I'm going to get a P star hat T minus P T minus 1 hat. So this basically is the bridge between reset prices and inflation. Um, so what we have to do next when we derive the Phillips curve, the next step is quite like I don't even need to do it for you guys. You just need to substitute the linearized pricing rule. Okay, so this one, the one we did before, you need to substitute it into this, which was the linearized version of the index, and we converted it into in form of inflation. And when you do that, the next step is to replace the marginal cost with the output gap, okay? um, and you'll obtain the Phillips curve. So you'll obtain the Phillips curve, which will look like this. Inflation is equals to some coefficient B, expected value of next year inflation, and some constant K into the output gap. Okay, so we've after you do these steps, you'll get the Phillips curve. So far we've learned how to linearize the optimal pricing rule and the aggregate price index. Now the final step towards understanding how we get the Phillips curve is where did the optimal price, how did we get the optimal price, right? Because I just stated the optimal price, but we didn't derive the optimal price. So the last step is to just understand how to derive the unlinearized version of the optimal price. So just take a 5 minutes break and we'll continue. Hey, I hope all of you enjoyed your break. So let's begin the last part of the derivation. Remember that the Phillips curve answers just one question, in which is how does current inflation depend on the expectations of future inflation and real economic activity. So we need price setting behavior under nominal rigidities. This is what the Keynesian economists have assumed. Remember, the old Phillips curve was backward looking and it was ad hoc. Okay, it did depend on the deviations of output from the long run levels. So we had the deviations of the output from its long run levels, but it depended on, it was, inflation was dependent on the previous year's inflation. The new Keynesian Phillips curve actually was forward looking and micro founded. It has again the deviation of output from its long run levels, but now in current inflation depends on future inflation, your expectations about it. The key assumptions is that prices are sticky. Each firm, period of firm can reset its price with probability 1 minus theta, and with probability theta, it must keep its old price. So if theta amount of firms are basically stuck with their old price, they cannot update their prices, and the rest are able to update the prices. Okay, firms don't know when they can reset again. Expected duration of a price is 1 over 1 minus theta. We have random price rigidity, not fixed contracts. When a firm is allowed to reset a price at time t, it chooses a price p star to maximize the expected discounted profits over the time its price remains fixed. So obviously, if you're not allowed to change price for the next 5 years, you will choose a price p star which is going to maximize your the discounted value of, or basically the present value of all your future profits in that time period. So what is the firm's objective? It is to maximize the expected profits, and this is basically just the discount factor. It's discounting. K stands for the number of periods price remains constant. We are just taking it from 0 to infinity. Let's suppose it's actually not infinite because you are going to update your contracts, but it's just a way that they've set it. And theta k is the probability the price survives k periods. Okay, the another thing that they're going to give you is the demand for each firm's good. So this is ith firm's demand, which depends on the price ratio, and it is constant elasticity of substitution. So this shows constant elasticity of substitution. If the relative price is high, demand is going to be low, which makes sense. If there are, suppose there are 5 firms, selling similar products, then if relatively your price is higher, then the demand for your good is going to be low, even if there is some distinguishing factor between your the product that you're selling, but there's still, like, you're still going to suffer from less demand because of a higher relative price. Okay, the profit is given of each firm is basically total revenue minus total cost, and now the objective is to maximize the profit. So let's start doing this. So this is the final part. Take deep breaths, and you should be happy that, like, I've wasted so many hours trying to figure this out. I don't know why it took me so much time to figure it out. Actually, the linearization that we just did, that kind of was mind-blowing for me, because I was like, whoa, what's happening here? Anyhow, okay, this is the output of each firm, the demand faced by each firm. We'll substitute this here. Okay, and we have this here. Actually, let's substitute the demand for each function over here. This, which was it? This is it. Yeah, substituted. There's a minus sign in between. Minus sign. Okay. So we can take this as common. Yeah, both of them have this expression, y t plus k for each firm, and we'll be left with this, the price ratio from the first expression, and then the marginal cost from the second expression. Okay, so we want to find the optimal price, right? So therefore we want to take the derivative and put it equals to a 0, and we'll be able to find the optimal price. So we want to find p star. Okay, so let's take the derivative with respect to p star t and then put it equals to a 0. So on the right hand side, the power will get multiplied. So we'll have a minus epsilon. Then we have the price ratio p hat t over p t plus k power minus e minus 1 and yt plus k. Let's just keep it that way. Oh, actually, I was about to just treat this as a constant, but there's a p star here as well, so we'll have to use the product rule, unfortunately. So, okay. So let's create this into our u and this into our v. So therefore, the product rule is going to be the derivative of u into v plus v, the derivative of v into a u. Okay, so I'm taking the derivative of u, so the power gets, and the derivative of the internal expression is a 1 over a pt plus k. So this is the derivative of u, and we should write v as it is. So v comes as it is. Okay, then u as it is. So let's just write u as it is, and the derivative of v is just a 1 over a p t plus k, because that's the constant being multiplied by p star, and there's no p star here. Okay, now what? We can take this as common. Both of these expressions have this. Yeah, so let's do that. We can take yt plus k over a pt plus k as common, and I'll get a minus epsilon p star over pt plus k over to the power minus epsilon minus 1, and then this is getting multiplied by p star over pt plus k minus marginal cost t plus k. And in the next we have a plus, and this is what's being multiplied by this expression. Okay, now what? Okay, let's open this up now. So this stays there as it is, and we're multiplying through, so we'll have a minus epsilon e p star over pt plus k, and minus e minus 1 plus 1 is just a minus e, so this becomes a power minus e. Then we'll have a plus e into the marginal cost t plus k. Great. Then we have this expression. Yay, this kind of looks nice, because then I can take this as common now. If I take that as common, I'll have, let me just write all of this here, and if I take this expression as common, I'll have a minus epsilon here and plus 1 here, so a plus 1 minus epsilon. Yeah, this looks okay. So yeah, looks reasonable. So should I take this inside or not? Maybe I should remove this from here. What will I have to multiply over there then? Oh, I forgot to multiply this expression with e. Oops, my bad. Let me fit that in. E, because this whole thing multiplied by this, and this whole thing multiplied by that. So I just forgot this expression gets multiplied by marginal cost as well. Okay, thank God, not too big of a mistake, and I got it on time. Don't know how people like do mathematics on paper anymore, because I seem to make so many mistakes which are easy to handle when you have it's easy to rub out when you can edit so easily. Okay, so let's take this expression out as common. Okay, so if I take this ratio out as common, I'm gonna be left with a 1 minus epsilon into a p star t over a pk plus t plus k, because I know minus e minus 1 plus 1 is just a minus e, and this is what I have, a minus e. And then on the right expression, I'll have a plus epsilon marginal cost t plus k. Okay, so this is the derivative of the profit function with respect to p hat p star. Okay, and this was the firm's maximization problem. So our firm's problem was this was the first. Let's take the first order condition now. I think we can actually, because it's an infinite horizon dynamic problem, we can also solve this making a Bellman equation. But I think it's fine right now, even if I just take the first order condition and put it equals to a 0. So I'm trying to find the optimal price. So therefore, I need to take the derivative of the objective function p star t. This was the objective function, and put it equals to a 0. Okay, so the summation is on k, so this goes right here. The derivative will go inside. We're assuming continuous functions, expected value of this. Okay, good enough. Okay, and we've already derived the derivative of the profit function with respect to price. We just need to put it there. So we have this, and now the expected value of this whole expression. Yeah. And when we want to put it equals to, oops, yeah, it's fine, a 0. Okay, let's open up the brackets from 0 to infinity, p theta power k, and then we have a y t plus k, and we'll have a p hat t minus epsilon, and in the denominator we'll have, okay, this has a power 1, the next has a power e minus 1, then we have a plus 1, so it's just a 1 minus e. So pt plus k is power 1 minus e, and multiplied by 1 minus e, plus we'll have a beta k, b theta k, and again this actually remains pretty much the same. We'll have a yt plus k, p star t e minus 1, but in the denominator we'll have a pt plus k, and we're just going to get a minus epsilon here, and multiplied by epsilon marginal cost t plus k is equal to a 0. So now we can just put the summation sign on things that wherever we have a k, the summation is going to apply on that. So in the first expression, I'm going to take 1 minus epsilon outside because there's no summation over there, and we'll have minus e over here, summation from k 0 to infinity p theta power k p t plus k, and this is just epsilon minus 1, and yt plus k n plus epsilon summation b theta power k, and we have marginal cost t plus k, and we have p p star, what was it, minus e minus 1 p star, and there is a, let me just, oh my god, it's not fitting here, let me reduce the size. This is with the pt, and with the pt plus k we have a minus epsilon is equals to 0. No, sorry, it actually is a positive because I'm taking it up in the numerator, so it'll become a positive epsilon. Okay, so now this expression is equals to a 0. So let's take one expression onto the other side. So let's just put an equality sign here, and we can write this as epsilon minus 1, okay, because we'll have a negative sign. Okay, so remember the summation is actually not on the star value because there's no k here, so this can go outside the summation, this can remain inside. And now if I divide through by, you can divide through by, oops, what the hell, by p star t power minus e. I'll have a p star t minus e. So therefore on the left hand side you'll get this expression. What am I doing? The p star gets cancelled out completely, so this goes away. And on the right hand side, we're only going to be left with a p star. So it's easy to make it the subject now. So this goes away, this goes away. We're just going to be left with a p star t. Yay! This is our optimal price. We just need to make it into the subject now. I'll have a p star t equals to this divided by this whole thing. Where is it? This whole thing. Obviously without this. Oh wait, this was to the power 1. Alright, so I'll have a minus 1 over here, a minus 1 over here. So let's just take the reciprocal. The optimal pricing rule is going to be this divided by this. And yay! So we now have the, remember this is the Calvo optimal pricing rule, which is not yet a Phillips curve, okay? This is the non-linearized version, which we have to linearize. Okay, and what about the pricing index? That's basically just given. So the aggregate price index under Calvo pricing is given as pt power 1 minus epsilon is equals to integral from 0 to 1 pt of the individual firm power 1 minus e di, and this basically becomes a theta pt minus 1 power 1 minus epsilon plus 1 minus theta into p star t1 minus epsilon. And again, this is the non-linearized version, and we ended up having to linearize it before we could substitute the optimal price into the linearized version of the price index to obtain the what do you call the Phillips curve. So as a recap, let me start doing a recap. We wanted, the whole lesson was about how to derive the new Keynesian Phillips curve. Okay, and for that what we had to do was we had to find a linearized version of the optimal price. Okay, and we had to substitute it. So I'll just put it into the linearized version of the price index. Okay, and once you do that, you will get the new Keynesian Phillips curve. The only issue was that you have to maximize the discounted value of profits, and that basically gives you the non-linear version of the optimal price, and you have to linearize it. So this is basically one step. This is the outcome has to be converted again into a linearized version. That's the second step, and the price index is just given. So the index is provided. You don't have to derive that, it's given. All you need to do is, because it's non-linear, you just have to linearize it. So that was a summary. I totally empathize with the fact that this lesson was horrific. Even while recording it, I was having a lot of brain fog because I don't know, I'm just talking and solving math at the same time is, I don't know, a bit complicated. So this is enough for today. If you have any questions, or if this was a really bad lecture and you guys think I should re-record it, I don't mind. Most probably the second attempt at explaining all of this would be better. But if you do understand it, that's good for you. And hopefully I will see you in the next one. Yeah. Wow, this was long. Take care.